We've talked about how to model different electric circuits in order to come up with a simpler equivalent circuit. But the reason why we're trying to develop a simpler model is for a specific purpose, to try to optimize our circuits in one way or the other. There are two primary types of optimization that we try to do as engineers. Number one is optimizing for maximum efficiency. This is the sort of thing we usually do if we're working on a big power system like the national grid. In that case, we want the maximum efficiency possible because we're sending so much energy through the system that any inefficiencies that we have could cost a lot of money just by the sheer volume that we're sending through. The other type of optimization is for maximum power transfer. This is more for lower power situations where the power is limited and thus we want to make the most of it. One example of this is if you have a stereo that is hooked up to a speaker. The stereo itself doesn't have a whole lot of power output, comparatively speaking, and that stereo is plugged into your wall socket, and so the actual efficiency of the stereo isn't a huge issue. If your stereo is a little bit more efficient or a little bit less efficient, that's probably not a purchasing concern as much as how well the stereo works and how it sounds. On the other hand, though, that stereo has to send power to the speaker, and the speaker is the thing that you are going to hear and the thing that you are going to make your decision about the quality of that stereo. And so in this sort of situation, an engineer is trying to make sure that we have a maximum power transfer going from the stereo to the speaker so that the speaker can be as loud and produce as good of a sound as possible. And so in that situation, we don't care so much about the efficiency of the stereo itself, but how well that stereo is able to transfer power to the speaker to be converted to sound. For our speaker or any other load, we can imagine that that load is connected to some sort of network, and that network will assume here will be resistive, containing independent sources, and it will be connected by two terminals. So similar to the two-prong plug that you would plug into your wall socket would connect to a much more complicated network behind it. For right now, we're going to assume that the load is resistive as well. What we've seen previously is that if you have a complicated network, we can represent this as a Thevenin equivalent circuit. So we have our Thevenin voltage and our Thevenin equivalent resistance connected to our load resistor. And what we're interested in here, again, is the maximum power transfer. We have a supply circuit here, we have a load there, and we're trying to make sure that we have a maximum amount of power that's being transferred from that supply circuit to our load. And so if we're looking for the power being transferred to the load, well, we can look at the current in the circuit. The current in the circuit that is being applied to the load is going to be the total voltage, which is coming from the Thevenin source, divided by the total resistance, which is these two in series with one another. And so if we have an expression representing the current in the circuit, then the power being transferred to the load, the power being dissipated by that resistive load, is going to be I squared R, where I is this value that we had before. We square it and we multiply by the load resistance. What we're looking at here is we're assuming that the Thevenin voltage and the Thevenin resistance are fixed for a given source circuit. Whatever system you have here that you're plugging into, we're assuming that it already exists and it already has a fixed Thevenin voltage and resistance, and so we're trying to see how we need to adjust the load resistance in order to maintain that, to maximize that power transfer. And so if that's the case, then the power being received by the load would depend on constant values, and it would depend on this load resistance. So if the power delivered to the load is a function of the load resistance, then we should be able to maximize that function in order to find the maximum power that we can deliver to the load. If we want to maximize a function, the way we do that is by taking the derivative of that function and setting it equal to 0. Recall this is the equation that we just had for the power delivered to the load. Power is I squared R, and this was our equation for the current I passing through the load. Because we're trying to take the derivative with respect to the load resistance, what we can do is distribute the square, and we can square this term and square this term, and then I'm pulling that Thevenin voltage out front because that's a constant. That's not going to do anything when we take our derivative. Then we take the derivative of the load power divided by the with respect to the load resistance. This is again our constant that's just sitting up front. Here we have a fraction where we have our variable in both the numerator and the denominator, so we have to apply the quotient rule. We apply the quotient rule here, and now our derivative should be set equal to 0 to find the maximized value. This is a constant. That's not going to equal 0, so we can throw that part out. We're assuming here that these values are both finite and non-zero. The resistance is a real value that has to have some finite amount to it. That's not going to be 0 or infinity, so we can throw that term out as well. And so if this whole derivative should equal 0, it should mean that this numerator here should equal 0. Well, if this whole thing equals 0, we see again that we have a common term. This common term is non-zero. It's some finite value, so we can divide out that finite value as well. And in so doing, we have R Thevenin plus RL minus 2RL equals 0, this equation here. If we have RL minus 2RL, that means we have negative 1RL left. And if we have R Thevenin minus RL equals 0, that tells us that the value of the load resistance that we need to have should match the Thevenin resistance. And in fact, you'll see this in headphones and antennas and speakers and such, where the internal resistance of that circuit element will have a fixed given amount, so that its load resistance matches the R Thevenin, the standard output resistance that you'd have for a headphones jack or a speaker plug, that sort of thing. We assumed that R Thevenin was fixed because the R Thevenin is coming from the supply circuit that is powering our load. However, if we're on the other side of the coin and we are designing that supply circuit, we might want to look downstream and see what our supply circuit is going to behave like when it's supplying a load. And so we want to look now. Let's imagine R Thevenin is not a constant. Let's imagine R Thevenin is variable for a fixed load, and we'll see how we can maximize the power delivered to the load in that case. So same idea, we have the power delivering to the load is the same equation we had before, but now we're assuming that the load resistance is constant and that we can change the Thevenin equivalent resistance of our supply circuit to try to maximize that power. So again, I've taken the original circuit and I've rewritten it here. These are both constants, and my variable is R Thevenin. We're going to see how to maximize the power output per R Thevenin. So if we take the derivative here, these two terms are constants, so those just sit out front. Here we have our variable inside of a power, so we have to do a chain rule there. And we would like to set this thing equal to 0 to maximize the output, but we see that these values here are positive. Those are true numbers that could be measured, and they are amounts, so they're always positive. Resistances are always positive as well. These are finite numbers, and so if we take finite numbers to some power, this is also some positive amount, and then this times a negative 2 is a negative amount. So if we have a positive times a negative times a positive, that is a negative overall number. It's always going to be less than 0. So our derivative here with respect to R Thevenin is always negative. That means that as R Thevenin gets bigger, the power output gets smaller for a fixed value of the load output. So the bigger the output resistance is, the bigger the Thevenin resistance is, the less power output less power transfer you're going to have to the load. And vice versa, the smaller you can make R Thevenin, the larger the power transfer is going to be. So in this, what this is telling us then is, from the supply side, you want to try to minimize R Thevenin as much as possible. And in the previous calculation, we saw that whatever that minimum output resistance is, you want to match your load resistance to that resistance from your supply circuit. The only exception to this is perhaps there's an industry standard that kind of splits the difference, where there's a industry standard output or equivalent Thevenin equivalent resistance that you'd want to match your industry standard load resistance to make sure that you'd have interchangeability between systems.